Here's a question for you. What is the molar enthalpy of combustion for methane? What I'm asking is, what is the change in enthalpy for 1 mole of methane in this reaction? Well, as you can see, the enthalpy change of negative 802.5 kilojoules already applies to 1 mole of methane. So the molar enthalpy of combustion for methane and the enthalpy change for methane in this equation both happen to be the same, negative 802.5 kilojoules. Written like this. Again, the subscripted M is optional, and I only use it to clearly differentiate between enthalpy change and molar enthalpy change. You should be aware, though, that Alberta Education, who authored the diploma exams and on which my unit exams and final exam questions are based, do not employ its use. The molar enthalpy of reaction for carbon dioxide is also negative 802.5 kilojoules per mole. Now, what do you imagine is the molar enthalpy of reaction for oxygen? Well, 2 moles is negative 802.5 kilojoules. 1 mole would be what? Half the amount. Negative 401.25, rounded to 0.3, kilojoules per mole. And for 2 moles of water vapor, the molar enthalpy change is also negative 402.3 kilojoules per mole. So the change in molar enthalpy for a substance is determined by dividing the change in enthalpy for the reaction by the number of moles of the substance. Another way to show the same expression as it's presented in your text is making the change in enthalpy of the reaction equal to the molar enthalpy change of a substance multiplied by its mole quantity as written in the balanced chemical equation. Using this equation, let's have a look at this question. Use the thermochemical equation below to calculate the enthalpy change when 35.5 grams of butane is completely combusted. We're asked to calculate the enthalpy change. In the equation, we see that negative 2,877.3 kilojoules is the enthalpy change. So is that not the answer? No, since negative 2,877.3 kilojoules is the enthalpy change associated with 2 moles of butane, and not the 35.5 grams as the question is asking. So our strategy is to first find the number of moles 35.5 grams of butane amounts to. Then find the molar enthalpy change for the combustion of butane. In other words, find what the change in enthalpy for the reaction would be if we had 1 mole of butane instead of 2. Finally, multiply them together so we end up with the enthalpy change for the reaction of 35.5 grams of butane. The number of moles in 35.5 grams of butane is 0.6105 moles. Now I realize your calculators will show more digits. Write down the number as it's shown on your calculator without rounding to 1 or 2 digits more than what's expected in your final answer. However, leave the entire number in your calculator to be used for future calculations. It is therefore critical to learn how to use the memory feature of your calculator. Only a final answer will get rounded. Next, the change in the molar enthalpy of reaction of butane is the delta H as written in the equation. It's a negative value, remember, because it's a product in this reaction, divided by the coefficient next to the butane, which is 2. We get negative 1,438.65 kilojoules per mole. Multiply the two calculations together. Use the values still in your calculator, not the truncated ones you've written down on your page. The moles cancel out, and you're left with the enthalpy change created by combusting 35.5 grams of butane, clearly stated, rounded to the correct number of significant digits, and showing the correct units. Calorimetry. The need to determine the energies released or absorbed from chemical reactions has many applications. Firefighters decide how best to fight a fire based on the exothermic properties of different combustible materials. Dietitians plan balanced diets around the exothermic properties of foods as they are processed in our bodies. Designing an engine will incorporate the exothermic properties of different fuels. Calorimetry is a way scientists can quantify the amount of energy released or absorbed during a chemical reaction. It involves the use of a calorimeter. A calorimeter is an isolated system. An isolated system is one that prevents the transfer of matter and thermal energy into or out of the system. The insulated walls contain a specific amount of water surrounding the chemical reaction, as shown in the schematic diagram here. A thermometer and sometimes a stirrer completes the calorimeter. The idea is, as a chemical reaction proceeds in the water and energy is released, the water absorbs that energy, increasing its temperature. Assuming a negligible energy exchange between the walls of the calorimeter and the outside, the temperature change registering on the thermometer is a measure of the change in kinetic energy of the water molecules. And this change is considered in this course to be exactly equal to the chemical potential energy being released by the chemical reaction. Likewise, if the reaction is endothermic, energy being absorbed by the chemical reaction will be equal in magnitude to the drop in kinetic energy of the water molecules, indicated by the thermometer as a drop in temperature.